Thank you very much, everyone. My name is Ethan Quist. I'm a robotics engineer, not a surgeon. I work for the Telemedicine and Advanced Technology Research Center. I'm the Deputy Chief of the Medical Robotics and Autonomous Systems Division there. We're part of the United States Army Medical Research and Development Command. I'm here to talk about two different projects that we have at TATRC involving telesurgical capabilities and really how we're investigating ways to overcome the military challenges that you see in the operating environment for telerobotic surgery. The first project that I'm going to be speaking about is really focused on developing a semi-autonomous control strategy to work in the military operating environment. And the second project that we have is a follow-on project that's more directed towards direct teleoperation and latency mitigating techniques. I have nothing to disclose, and these views are my own and not that of the government. Give it another second here. In recent conflicts in the Middle East, the United States Army and military forces have had a near dominant control over the airspace, which has allowed the military community, military medicine community, to follow the doctrine of the golden hour, which, when a casualty has an injury, that they are, evacuated to surgical intervention within the first hour of their injury. But what we know from possible future multi-domain operations, there's going to be a challenge to that golden hour doctrine. And with a larger disbursement of troops and medical personnel and a possible denial and delay of evacuation, we're going to need to have advancements in our lower roles of care and technologies to help our military medical personnel there. We're going to have forward deployed surgeons that are going to have to take care of more casualties for longer and have to perform more complex and specialized surgeries at those roles of care. The military operating environment is commonly characterized as disrupted, disconnected, intermittent, and low bandwidth, the DDIL environment. And for any technologies that we're going to develop to help out our forward deployed medical forces, we really have to make them operate in those DDIL environments. So I'm up here on the stage because a lot of the challenges that the Army is facing is obviously very common to surgery in space and the United States Space Force as well. This issues of DDIL environments is very common from both our land operations as well as our space operations. The two projects that we have been working on, the first one is involving developing a semi-autonomous control framework for us to be able to provide telesurgical assistance in those DDIL environments. This project concluded last March in an animal study that I'll be talking about later on in this presentation. Our second project is looking more directly into the teleoperation use case, and if we can develop latency mitigating techniques such as adaptive motion scaling for us to mitigate that latency under direct teleoperation. Here are our two hypotheses that we had for our two studies. The first, we really were trying to accomplish a proof of demonstration animal study for our semi-autonomous control framework, while our second project, we're looking to have a more rigorous non-inferiority study looking into how direct teleoperation compares to the standard of care currently. I want to emphasize now that the research that we're conducting at TATRC is not to replace deployed surgeons, but to augment them with assistive tools and technologies, such as teleoperative devices, so that way more specialized assistance can be there for them downrange using these tools. We're also looking into not necessarily just your typical damage control surgeries, but some of those specialized surgeries such as vascular surgeries, urology, ocular, as well. The effort that we have is very collaborative. We have industry partners with SRI International, as well as academic partners from the University of California, San Diego, University of California, Berkeley, and University of Chicago. At the start of our project, we had to design a novel telerobotic platform that was able to operate both in teleoperative control as well as semi-autonomous control. Our partners at SRI International, through previous work, had developed the TORS robot, for the Department of Homeland Security as a research effort into explosive ordnance disposal. And we found that explosive ordnance disposal, the requirements for that to be highly dexterous and teleoperative, translated very easily to the surgical space as well. So what we did is we modified the TATRC robot that was built by SRI to, we redesigned the arms for them to equip the Da Vinci Xi line of surgical tools. And this system operates using a Oculus Rift virtual reality headset. The surgeon donning the VR headset is able to see through the robot's stereoscopic cameras that are on board. The platform itself weighs 15 pounds. It can fit in a backpack and draws relatively low power. It can be set up and taken down very quickly, so we see this as a platform that is a good use case for being able to set up and tear down quickly, which are requirements you would need in a forward deployed setting. The picture on the right there is inside the operator control unit, which is what the surgeon will see when they're donning the VR headset. And we've designed it to be very modular. So in the center there, you see through the eyes of the stereoscopic cameras. But to the right, you also see what we call the puppet version of the robot. So you can see where the arms and the robot position is at all times. You can also pull in different module windows, such as vital signs from the patient, any situational awareness within that virtual reality environment for the remote surgeon to see. Next, we had to invest a lot of our time into developing surgical perception. One of the other constraints that we have in the military operating environment is that low bandwidth constraint. So our solution to that was to rely heavily on surgical perception technologies that would be local on-site at the robot using camera systems and different structural systems. So we've developed perception technologies for object detection and segmentation, starting first with the FLS pegboard, being able to detect and segment that, but then we advanced it to also detecting vessels in the surgical scene and segmenting the vessels and finding their vessel edges. Next, to really reach that semi-autonomy use case, we knew that we needed to make a digital simulation environment of the surgical scene. So we did this through those perception technologies and tool tracking technologies that we've developed. And this way, if the remote surgeon is operating in the digital simulation of the scene and the local robot is operating that same digital scene, then we can reduce the amount of bandwidth that's required to transmit from the remote site to the robot site, since only the delta changes in the scene, since it's all digital, need to be passed over that network bandwidth. So we can reduce the size of current systems that require 4K video to be sent over a network, which can take gigabits per second, down to kilobits per second if it's really only the delta changes in a digital environment. Next, this slide showing our framework for that semi-autonomy control. Our partners at SRI International developed this, and they named it the intent-based control. And basically what this does is it separates the high-level aspects of what the remote surgeon does and the low-level aspects of what the robot does. So all of the clinical decision-making is still up to the remote surgeon as they're making decisions of where to grasp a vessel, where to cut. That's all still up to them in that digital environment. They go ahead and use the VR controllers to make those movements. And instead of the entire path to that vessel spot, only the intent and the high-level commands are sent over the network to the robot, and the robot actually is able to carry out all the low-level planning. So the robot's actually, from there, interpreting what the high-level commands and then executing the path planning that it would need to go from point A to point B, which is robotic systems are very good at. So what this does is, for one, the robot does not need to have any sort of higher-level intelligence of a procedure, as it's really just executing, interpreting what those higher-level commands are coming from the remote surgeon. And two, what this does is it virtually eliminates latency as an issue for overshoot and tool collision errors, as the latency is not a problem from the high-level commands sent from the robot, from the remote operator to the robot. It's in real time that the robot's calculating how it makes those, path planning and trajectory planning to go from point A to point B. We accomplished this for our animal study by using OptiTrack cameras. So with the OptiTrack cameras on this surgical site local to the robot, with fiducials that are also on the arms of the Taurus M, as well as on the tools of the surgeon, that information was able to be passed back to the remote surgeon through this framework. So that way the remote surgeon, without having a full visual of everything that's happening on the surgical scene, can see those changes and those updates of where the tools are, where the robot is, so it understands the procedure and where it is, step by step as it's moving through a procedure. This past March, or last March, we conducted an animal study at the University of California, San Diego, where we were able to use our Taurus M robotic platform to perform a temporary vascular shunt placement procedure with both two surgeon control groups, as well as one surgeon and one teleoperated assisted remote surgeon groups under both direct teleoperation and our semi-autonomous control network. The trials that were done with the robot were done under various levels of latency. And as you can see in this picture, on the left side you have the semi-autonomous control framework where we have the OptiTrack cameras that are tracking the fiducials on the robot as well as the fiducials on the local surgeon's tools. And on the right, you see the direct teleoperation setup. As you can see, the robot takes up a very small footprint in the operating room, is able to maneuver around the bedside very easily as it's on wheels. Just going to go into a little bit of an overview of the data that we collected from that first animal study. We were able to conduct 55 trials. I want to reiterate, though, that this was just a proof of concept animal study for us to show our semi-autonomous control framework, and we did not do enough trials to get any sort of true comparison with statistical analysis, but just it's observational data that we have so far. The number one metric that we were tracking was success of the procedure of the temporary vascular shunt placement. We measured that as blood flow across the shunt measured by a Doppler sound device. We are happy to present that we are 100% successful with all of our trials that involved the Taurus M telerobotic system. Looking a little deeper into some of the secondary metrics that we had for the procedure, we were also measuring the total time for each of the procedures as well as the errors, including overshoots and tool collisions and misses. What is first obvious to see is that as we insert latency for the direct teleop trials, you can see that as latency increases, both the time of procedure increase and the errors increase. But what's very interesting is that as latency increases from 0 seconds to 6 seconds of latency for the semi-autonomous trial, the system did not seem to be affected by that latency, as actually both errors and time of procedure dropped. We think that the time of procedure dropping was actually more due to a learning factor. And again, we did not run enough trials for this to be statistically significant, but it's very good data for our observations to know that we, one, feel that we have successfully proven our hypothesis that this was able to be a proof of concept for our semi-autonomous control and also warrant further research into this type of work. Some key takeaways, again, is that we believe that we've proven our first hypothesis that semi-autonomous control can be an effective countermeasure to improve safety and efficacy in delayed environments for telerobotic surgery. We also were proud that we had a 100% success rate with performing the temporary vascular shunt procedure in assistance with the telerobotic robot. And just to give a little note of the levels of latency that we were using, our semi-autonomous control framework was able to operate in levels of latency that would have been impossible for a direct teleoperation, as we're using 6 seconds of latency in a simulated environment in the network, which is representative of 3 times past the distance from Earth to the moon. We have follow-on studies that are ongoing right now at TATRC. The follow-on study is more directed at teleoperation control. We started this project at the advent of Starlink and in 5G advancements in the communications industry, that we believe we wanted to investigate kind of a different path down of how can we improve direct teleoperation and look into ways that we can mitigate the effects of latency if that's a near or closer win for being able to deploy these types of systems. So what we're looking into is not the simulated latency that we did in our original trials in our previous project, which was all static latency. So if we put it to 2 seconds of latency, it would be static for the entire procedure, which obviously is not realistic. So we're looking into actual real-life dynamic latency, which is going to be unpredictable and random, as it's going to go, have spikes and valleys in the level of latency that's experienced by the robotic surgeon. So we're looking to mitigate that with techniques such as adaptive motion scaling inherent in the network. We're going to be conducting a non-inferiority study at the end of this project next year, where we're looking at, how does this system compare against the standard of care to surgeons working on the vascular repair surgeries with a teleoperated assistive platform, the TATRC. We're going to be doing that at various levels of dynamic latency, as well as with and without the adaptive motion scaling. We're also introducing not just the temporary vascular shunt procedure, but we're also going to be including a microvascular anastomosis, as we see this platform being able to project in the assistance of more specialized surgeons, so that way they can assist general surgeons who may be deployed that can do the operations, but would benefit from the experience of specialized surgeons in assistance with them. I'll just talk a little bit of the adaptive motion scaling that we're looking to develop and implement into our system. In short, it's going to be detecting the network delay that's experienced on the network between the robot and the remote surgeon, and it's going to adjust the motion control gains that will be experienced, which really, as there is an increase in delay, there would be a decrease in the motion ratio between the movements that the remote surgeon does to the movements of the robotic system itself. We're going to build it a little bit more complex than that simple explanation. It's going to have built off an AI model that's also looking to minimize the errors that it's kind of going to see through controlled studies, but also try to maximize the time for procedure. So trying to find that right balance in between the two. And we're building this off of profiles of surgeons that are using this system, as surgeon to surgeon might have a little bit of different profile for how they like the robot to operate. In conclusion, we're very happy to report our successful animal study last year of a proof of concept for our semi-autonomous control framework. We believe that this research has opened the door for ongoing and future research into telerobotic surgery for the military. The government now owns multiple platforms that are ripe and ideal for telerobotic surgery research with the TATRC platforms. I also want to acknowledge that this was very much a collaborative effort with a lot of different government partners, industry partners, and academic partners all across the country. And lastly, I just want to acknowledge that over the past 4 years, our academic partners have done a lot of work advancing the cutting edge of telerobotic surgeries, and I'm able to publish 14 different publications throughout this funded research. I want to thank you for your time.